Welcome to The Explainer. Today, we're diving into the tiny secret that powers basically everything in our digital world, the semiconductor. It's the unsung hero tucked away inside your phone, your computer, even in spacecraft, and we're about to uncover the atomic level hack that makes it all work. So here's how we're going to tackle this. We'll start with the real basics of how electrons move, then we'll uncover the secret rules that they all follow. After that, we get to the fun part, learning how we can hack those rules and see how that one simple trick literally built the modern world. All right, let's jump right in. To really get what makes a semiconductor so special, we first need to understand what it's not. You see, when it comes to electricity, materials pretty much fall into one of three camps. So you've got your conductors, like copper wire. Think of those as a wide open freeway. Electrons can just zoom along with no problem. Then you have insulators, like rubber, which are the exact opposite, a total gridlock. The electrons are just stuck. But then there are the semiconductors. They're the interesting ones. They're like a city street with traffic lights that we can control, turning them green or red whenever we want. Now, the physics behind those traffic lights is something called the band gap. The easiest way to think about it is like an energy toll. For an electron to break free from its atom and start moving around, it has to pay this toll. In a conductor, the toll is zero. The gate is always open. In an insulator, the toll is just way too high for any electron to pay. And this is the absolute key. Semiconductors are in that perfect sweet spot. Their energy toll is just low enough that we can give electrons a little push to get them moving, but it's also high enough that they won't just flow all on their own. It's this just right Goldilocks zone that makes them perfectly controllable. Okay, so we know we can control these electrons, but what's the rule book they're all playing by? What's governing their energy to begin with? Well, that brings us to a concept that's like the ultimate gatekeeper, the Fermi level. So in plain English, the Fermi level is basically the default energy setting for all the electrons in a material. You can think of it as their home base or their starting line before anything else happens. And this is the perfect way to picture it. Just imagine the Fermi level is the surface of an ocean. For an electron to actually do any work, like become part of an electrical current, it has to get enough energy to jump up above that water level. So where that sea level is set, well, that changes everything. So if the band gap is the toll and the Fermi level is the starting line, it just makes you wonder, right? Can we rig the system? Can we actually move that starting line to make it easier or harder for electrons to get going? Oh yeah, the answer is a huge yes. And get this, intentionally messing with it is probably one of the most important breakthroughs in all of modern physics. We figured out how to become the traffic cops for electrons. We do this with a process called doping. Now, it sounds a little shady, but all it means is that we're carefully sprinkling a few atoms of a different element, an impurity, into our perfectly pure semiconductor crystal. And this tiny little change makes a world of difference. Doping gives us two brand new flavors of semiconductor. If we add one kind of impurity, we create P-type material. P for positive, because it ends up with these little empty spots or holes where an electron should be. Add a different kind of impurity, and we get N-type material. N for negative, because it now has a surplus of free electrons just ready and waiting to move. And this is the whole point of our little hack. Adding those electron holes actually lowers the Fermi level in the P-type material, and adding those extra electrons raises the Fermi level in the N-type material. Just like that, we've engineered two totally different materials with two different electrical personalities. Okay, so now we've got our two custom-made materials. One that's missing electrons, and one that has extras. So what happens if we just stick them together? Well, this is where the real magic starts. When we join them, we create something called a p-n junction. I know, it doesn't sound very exciting, but that simple little seam, that is the fundamental building block for diodes, transistors, and I'm not kidding, basically every microchip ever made. It's the heart of our entire digital world. Okay, so here's how this little wonder works. Right when they touch, some of those extra electrons from the N side rush over to fill the holes on the P side. This creates a little neutral zone right in the middle, a barrier that stops any more flow. But if we apply a voltage in just the right direction, a forward bias, we shrink that barrier and boom, the current flows. Now, if you reverse the voltage, the barrier gets even bigger and everything slams shut. It is a perfect, tiny, one-way valve for electricity. That's really the best way to think about it. We've used physics to build a microscopic, solid-state switch with absolutely no moving parts that lets us direct the flow of electricity with perfect precision. All right, so we've built a one-way street for electrons. Why is that such a massive game changer? Well, because from this one simple building block, we can create an almost unbelievable range of modern technologies. I mean, just look at this stuff. The lights in your room, the solar panels on a roof, the tiny components that keep your phone from getting fried, they all come from the exact same starting point, the p-n junction. Take an LED. We're just pushing current across that junction. And as the electrons from the N side fall into the holes on the P side, they have to give up some energy. And how do they pay that energy toll? By spitting out a little particle of light, a photon. Billions of those every second, and you get the bright glow of an LED. Now, a solar panel, it's literally the exact opposite process. Here, photons from the sun come in and smack the junction, giving electrons the energy they need to get knocked out of their holes and get pushed across the barrier. That forced movement of electrons is an electrical current. And just like that, you've got solar power. And then you've got Zener diodes, which are a really clever twist on the whole thing. Think of them like a microscopic safety valve for electricity. They're designed to block any reverse current, unless that current gets too strong. If the voltage spikes past a certain point, they open up just enough to let the dangerous excess current escape, protecting all the delicate parts of a circuit. So when you zoom out, you see it. This one elegant atomic level control over how electrons flow is the foundation for everything. You start combining these simple p-n junctions, and you get transistors. You combine millions of those, and you get the microprocessors that run our entire civilization. It's just wild, isn't it? Our entire technological revolution, all of it, came from this one atomic hack, learning to control a single common element. So it really makes you wonder, right? As our power to control matter gets more and more precise, what's the next material we're going to master? And what new world is that going to build?